Real pleasure to have a dynamic young new researcher who's visiting us, Xiang Liu from the University of Rochester, the Biostat and Computational Biology department there. She comes to us with kind of a really nice mix of specializations in her background. She has both a bachelor's and master's degree in computer science from China, then a master's degree at the University of Florida in computer engineering, and then a PhD and master's in statistics from the University of Rochester. Very kind of prolific amount of work that she's done, given that she hasn't yet got her PhD, which will be done very shortly. But she's done work in variable selection, which we'll hear about today, some semi-parametric regression models, cure rate models, survival analysis, longitudinal data analysis, latent variable modeling, and then her application areas are sort of in cancer research and biomarker evaluation. So it's quite broad, given that she's finishing up her PhD. It's very impressive. So and she's also received some honors and awards to this point. She got a Merck Quantitative Sciences Fellowship. She won one of the travel awards to the University of Florida's Winter Workshop last year, which is a really fabulous workshop they put on. And then this year she just got the IMS LAHA Travel Award to present at the Joint Statistical Meetings, her work. So it's a real pleasure to have you here. And her talk today is on some estimation in variable selection in partial linear additive models.
It's my great pleasure to visit the University of Miami and to present my research work. And the topic of my talk today is estimation and variable selection for partially linear additive model. Penalty-based variable selection has been well studied for parametric regression models. However, its extension to semi-parametric regression model, to the semi-parametric regression model is not trivial. In the past 4 years, I have been working on variable selection under the supervision of Dr. Liang, and we have proposed a variable selection method for 4 semi-parametric regression models. So we worked on the partially linear single index model. This work is in collaboration with Dr. Li and Dr. Chai, Dr. Li from Penn State University and Dr. Chai from UC Davis. This work was published in Annals of Statistics last year. We also worked on partially linear additive models. This is in collaboration with Dr. Wang from University of Georgia, and our work will appear in Statistics Sinica soon. And the outcome variables in partially linear additive models is continuous. In order to deal with discrete outcome variables, we've worked further and collaborated with Dr. Carroll from Texas A&M University to study generalized partially linear additive models. And this work has been recently accepted by Annals of Statistics. Motivated by a breast cancer clinical trial study, we are now working on cure models. This is a joint work with Dr. Penn and Dr. Tu from Queen's University in Canada. My talk today is mainly about the partially linear additive models, and I will also briefly introduce the extension to generalized partially linear additive models. And I hope you will get a general idea of penalty-based variable selection for semi-parametric regression models from my talk. So in my talk, I will first introduce a beta-carotene study as a motivating example. Then after I give you a brief introduction of partially linear additive models and the variable selection method, I will present our proposed estimation and the variable selection method for the plan. And I will also show you some simulation results and the application of our method to the beta-carotene study. And I will also briefly discuss the extension to generalized partially linear additive models. And at the end, I will end with a summary and my future work. So please feel free to stop me if you have any questions. So many epidemiological studies showed that there is a negative association between beta-carotene levels and the risk of cancer. People are interested in factors influencing beta-carotene levels in human plasma. So a large clinical trial of skin cancer prevention with beta-carotene provides us some information about the beta-carotene levels in plasma and some personal characters like BMI, age, or gender, and also some dietary factors including alcohol consumed per week and some cholesterol, beta-carotene consumed per day. So this information enables us to get some idea of the relationship between the plasma beta-carotene levels and personal characteristics and the dietary factors. So as first try, we consider linear regression models. We regress the log beta-carotene levels on all the covariates. And I listed the estimated coefficients in this table. So as we can see, I highlighted 4 covariates which have significant treatment effect in the linear regression model. And we also see there are 2 other covariates have some marginal statistical significant treatment effects. The remaining covariates have very big p-values. So this motivates us to think that we wanted to build a prediction model which only includes some important predictors. And that's why we wanted to consider variable selections. However, as we take a further look at the data and we fit a more general models, a generalized additive model which allowed the effect of each covariate using some non-parametric functions which do not apply the very strong assumption of linear relationship between covariates and the response variables. As we can see that it seems that the effect of the log BMI and the calories are kind of linearly related to the outcome variables. But for the effect of age and also the cholesterol, you can see that for age there is some S shape here, and for the cholesterol it's a concave curve here. So if we use the linear regression model, we might kindly capture this increasing tendency for the effect of age. But however, for the concave effect of the cholesterol, we cannot capture these patterns. So that's why in the linear model we have very high p-values and we miss this information. This motivates us to consider a more flexible model which allows some effects of covariates to be nonlinear. That's why we consider the partially linear additive model. So in a partially linear additive model, we have 2 sets of covariates. We model the effect of the covariates in the first set using some linear relationship, linear predictors. And then we use some non-parametric smooth functions to model the effect of the covariates in the other set. And so this kind of try to capture the nonlinear effects. And here the random error, we assume random error has a conditional mean 0 and a finite variance given all the covariates. And in order to make this model identifiable, we make the assumption that the expectation of each smooth function has mean 0. Yes.
So you do not require that the variance of epsilon conditional on x and z is constant. It could be a non-trivial function of x and z.
Yeah. Yes.
Okay.
So in the estimation of partially linear additive models, there are two classes or methods to deal with the non-parametric terms. And one is kernel or local polynomial regression, which can be incorporated with the backfitting algorithm or some profile procedures. However, the computation for this kind of method is computation cost is pretty high because you need to solve a large system of equations. And on the other hand, we can use polynomial splines to approximate the non-parametric terms. And after this approximation, the model becomes a linear model, and any variable selection method can be applied afterward, and also the computation is very straightforward. So that's why we consider the polynomial spline procedure in our work. And in terms of variable selection, there are two classes of methods. One is a subset selection, which we examine some candidate subsets and select the best one according to some criteria like archaic information criteria, Bayesian information criteria. And the best subset selection examines all possible subsets. So the computation cost is very high if we have a large number of covariates. Stepwise selection can kindly reduce the computation burden by considering one covariate at each step is added or deleted. However, the result is not stable. So that's why people propose the penalized likelihood method, which can simultaneously estimate coefficients and select variables. And Lasso is a pioneer work in this direction. And adaptive Lasso and elastic net made improvement on Lasso and tried to remove the bias and also to deal with highly correlated covariates. And finally generalized the idea of Lasso and proposed a more systematic framework of penalized likelihood and applied their method to generalize the linear regression models and the Cox regression models. And they also proposed they called smoothly clipped absolute deviation penalty function and showed this penalty function has some good statistical properties. So considering the advantage of the penalized likelihood method, we adopted the idea of Fan and Lee and adapted their method to our partially linear additive model.
Can you go back one slide?
Get back?
Yeah, one slide. So you said that backfitting algorithm is kind of intensive, right? So
no matter backfitting or profile, but for the local polynomial, it's quite intensive.
Okay, because there's a version of backfitting that Trevor Hastie developed some time ago where he included variable selection in the backfitting. He called it Brudo.
Brudo.
You know, and it actually can do a form of variable selection for things like additive models or generalized additive models. So I'd be curious. I mean, it seems very fast when you use it. So I mean,
okay.
Anyway.
When you say kernel regression, you mean Nadaraya-Watson, yeah? For instance?
For instance, no, it's like the moving average or something, similar to.
Similar, okay. Because I was thinking that splines break down quickly as dimension increases. Faster than Nadaraya-Watson does. And so I was wondering why you would use spline rather than Nadaraya-Watson.
So, yes, spline is spline, actually the disadvantage of spline is it captures some very globally, so you cannot have very sharp changed curves. In that case, you cannot use the polynomial spline, and you can use a local polynomial. But the reason we consider the polynomial spline is because of the computation consideration.
Oh, I understand that, but Naderai-Watson is a linear method as well, and localizes quite well too.
Mm-hmm.
So, and works better as you increase dimension. So I was just a little bit surprised at that choice. I mean, it's a good choice, but
Mm-hmm.
I was a little bit surprised. And I wanted to ask you about your next page.
Uh-huh.
And first of all, BIC and penalized likelihood are 6 of one, half dozen of the other, right? They're very similar.
Uh-huh.
The BIC is an asymptotic approximation that works pretty well,
Yeah.
and corresponds to a penalized likelihood. So I'm surprised that two essentially mathematically equivalent procedures,
Uh-huh.
one could be not stable and the other can be stable.
Okay.
I don't understand how that can be.
So actually, the thing is why this BIC best subset with BIC is not stable, because it's kind of a discrete process. You consider each subset individually and select the best one according to some criteria. And in the other hand, the penalized likelihood is trying to using some shrinkage process, which is a continuous process in terms of the Turing parameters. So it's kind of since it's a continuous.
The tuning parameter is just a hyperparameter in your prior,
Mm-hmm.
right?
Mm-hmm.
You're just doing priors. If you wanted to argue that adaptive prior selection, like empirical Bayes, is giving you a better performance and you're calling it penalized likelihood, and AI beating BIC, okay, that I would understand.
Uh-huh.
But I think that it's the fact you're doing empirical Bayes rather than full Bayes that's giving you the. But again, I find it surprising that an empirical Bayes would be more stable
Mm-hmm.
than a fully Bayes.
Yeah, so I think, did I list the, I think I forgot to list one literatures here. Yeah, there is a little, and I think also in Penalize paper, they also discussed why this method is better than this subset selection. Yeah, maybe we can.
I read their paper, but not recently.
Yeah, maybe we can discuss it later.
Fair enough.
Okay, thank you. Okay, let me. In order to give you a better idea of the penalized likelihood method, I will use the linear regression model as example. So this is a standard setting for linear regression model. And in the penalized least squares, we introduce the penalty terms on the coefficients and introduce this to the RSS. And we tried to minimize this whole thing. So here the P lambda is the penalty function, and the lambda is a Turing parameter, can be selected by data-driven method like generalized cross-validation, BIC or AIC. So if we use the L1 penalty, which is the constant times the magnitude, the absolute value of the coefficient, it's the Lasso method. And finally propose a scattered penalty, which can be written in this form. And consider the penalty plot here. We can see that the main difference between the scattered penalty and the L1 penalty is that the scattered approaches some constant for large coefficients. And this kind of can be used to remove the bias. So finally suggests that a good penalty function should have three properties: sparsity, unbiasedness, and continuity. So I will use a very special case to illustrate the meaning of these three properties. So let's consider a very special, the design matrix is orthogonal and normalized. Then for one coefficient, we can plot the estimate from the OLS, ordinary least squares, and lasso or SCAD. And we can see that if the OLS gets some small estimate less than some threshold here, then lasso will set the estimate to 0. Same for SCAD. This is the property called sparsity. And for if we consider SCAD, if estimate from OLS is quite large, then some threshold, then the SCAD will estimate the coefficient using the same value as the OLS. However, lasso is kindly shrink the values towards 0, and that's why there is some bias for the lasso method. So this property is the unbiasedness property. And the continuity. So you can see that these two curves are continuous. So you can think this x-axis in terms of the data, and it suggests that this estimate is continuous in data. So this is called the continuity property. So one more big advantage of the SCAD method is finally showed that their method has an oracle property. This means that the estimators of the non-zero coefficients are asymptotically normal with the same means and the covariance that they would have if the zero coefficients were known in advance. In other words, the estimator of the non-zero coefficients are as efficient as if we know the true model in advance. So that's the good thing. So that's why we proposed to approximate the non-parametric terms by polynomial spline. Then we get approximated linear regression models. Then we can select variables from the linear part by minimizing a SCAD penalized residual sum square. And the polynomial spline is kind of to use piecewise the polynomial functions to approximate a smooth function, and with some constraints on the nodes. The main message I wanted to point out is we can use this formula to represent the whole non-parametric part. And BZ here is the basis function, which can be calculated for observed covariates. And gamma here is the unknown coefficients. This is the thing we wanted to estimate. So if we put this approximation back into our model, we can see that our model becomes a linear regression model. So, as first, in order, in terms.
Why do you claim that this is global, in a sense? I mean, it's really where you lay down the knots determines how much locality you.
Yeah. So in our approach, we use equally spaced knots, and you can also have some variate to do some other knot selections. Yeah. So globally means we usually only introduce some small number of nodes, try to capture the whole patterns for the curve. Yes. Oh no.
I've got a question a bit later.
Okay. Thank you. So in terms of estimation, we can just define this residual sum square and to minimize it, over gamma and beta. And we showed that the estimate of beta has a asymptotically normal distribution in this formula. This is a variance for our estimate, and we can see there's a beta naught here is a true values for the coefficients. So it's unbiased and has some covariance matrix in this form. And in order to select variables from the linear part, we introduce these penalty terms on coefficients in the linear part, and we tried to minimize this whole thing, the penalized RSS, and we, as I said, we use a scatter penalty here, and also the lambda Turing parameter lambdas can be chosen by data-driven method like GCV, BIC, or AIC. We showed using our procedures, there is a square root n consistent estimate of beta, and if we decomposite the coefficients vector into two parts, the first part contains all the non-zero coefficients, and the remaining part has zero coefficients. Then our estimate for the zero coefficients will set all the coefficients to 0 with the probability approaching 1. And for in order to estimate the non-zero coefficients, we showed that our estimate has an asymptotical distribution like this. And take a close look at this, we can see that this asymptotic normal distribution only depends on the x1, which corresponding to the non-zero coefficients. And if you compare all this distribution to this one given, you can see that it suggests that our method also has an oracle property. That means it only depends on the covariance x1. It seems that we know the true model in advance. That's the oracle property.
What impact does the spline terms have here in terms of variable selection? So what intuitively give me some idea as to what they're doing?
So for the spline, right?
You're not selecting the spline.
Yeah. In this work, we didn't consider to select variables for the non-parametric part. The thing is, we use spline to approximate the non-parametric terms.
Correct.
So this enables us to select variables from the linear part. But we can also use a polynomial spline to get an estimate for the non-parametric terms. And we also showed that the convergence rate for the non-parametric terms can also reach the optimal rate in a fully non-parametric setting. And you can also find this part in our publication. So in order to demonstrate the performance of a method, we conduct a simulation study. And we generated observations from these partially linear additive models, and we considered two nonlinear functions here. And we allow X has 8 elements. We generated the 8 elements from standard normal distribution, but with autoregressive correlation structure with coefficient 0.5. And also the random error is from standard error distribution and is independent of the covariance. And we generated the covariance in the nonlinear part from uniform distribution. And the true value for the coefficient vector is like this. And we noticed that there are 5 0 here. This means the corresponding 5 covariates are irrelevant in this model, and we wanted to see how our method can identify these irrelevant covariates. And for these two non-parametric functions, we use one sine function for Z1, and we use something like the tick function for this the second non-parametric function. And as I point out, after the approximation, we can use any variable selection method. And so we want to compare the performance of SCAD, lasso, and the BIC. And we define some criteria to compare the model complexity. One is the average number of correctly identified irrelevant variables. And as I said, as we know, there are 5 zeros, so we want this number optimally to be 5. And also the larger the better. And also we calculate the average number of incorrectly identified irrelevant variables. And we want this to be 0 or as small as possible.
Okay, I'm going to go back to my previous question. So, so you're approximating G1 and G2 through these polynomial splines, so then you can assume you have essentially a big linear model.
Yeah.
Right? But you're not; those are not subject to selection. It's
Yes.
only the beta.
Yes.
part.
Mm-hmm.
So ultimately, why is this problem trickier than? I mean, once you do that approximation, you're just back to a linear model at that point. So what is going on behind the scenes when you stick that approximation in there to make this problem harder than just linear regression?
So actually the idea is quite easy, but or I should say straightforward, but the challenge is the theoretical proof for the polynomial spline is very hard. That's one of the challenges. And as you point out, we can also consider to select variables for the non-parametric part. And since in the polynomial spline approximation, several coefficients are corresponding to one terms, so we might need to consider some grouped lasso or some other method to take care of them together. And actually, I started this work about 4 or 5 years ago. So at that time, we only consider it like this, and there's still a lot of work can be done. So in other words, in terms of prediction accuracy, we define some model error using just the sum of predicted errors, squared errors, and we fit the full model, which means we include all covariates into the model and use the fitted full model as a reference. Then we calculated the relevant model error, which means for example, for SCAD method, we use the model error of SCAD divided by model error from the full model, and we will report the median of the relative models from our simulation. We have 100 replicates runs in our simulation. So this table lists all the criteria we wanted to see, and for different standard error, for random error, and for different sample size. And here the blue colors highlighted the situations that SCAD has the lowest median relative model errors. And the green colors highlighted the situations that lasso has the lowest median relative MRME. So this shows that SCAD, in terms of prediction accuracy, SCAD performs the best when the random error, the variance of random error is small, and also sample size is large. So it's on this triangle, on the triangle. And for lasso, lasso performs the best for large variance of random error and small sample size. So it's on this side.
You know, what might be useful is if you had a column that showed these prediction error estimates when you actually put in the correct functional form of those G1 and G2, because it's a simulation, so you know what they are.
Okay.
Then you can kind of assess what role your polynomial approximation is having.
Okay.
And it gives you a little bit better idea of how to tease out the effect of SCAD or whatever variable selection.
Yeah, that's a good suggestion.
Because ultimately, all of these models are wrong, right? So
Yeah.
any approximation you throw in there is wrong. So if you're generating prediction estimates from a wrong model, I'm not talking about the beta part. I'm talking about the G1 and
Yeah,
G2.
I know.
Those are wrong now because they're approximations. You're bound to be off, right? So you kind of want to see what role that approximation is playing.
Okay, yeah, thank you. So in terms of the model complexity, so I use the magenta color to highlight that the highest character is identified irrelevant variable covariates. And we can see BIC performs the best, has the highest numbers here, but also it also has the highest number of incorrectly identified irrelevant covariates. So this, in summary, this shows that the SCAD and the BIC have the best performance in our simulations. But compared to BIC, SCAD has the higher prediction accuracy by slightly increasing the model complexity. This means SCAD kindly include more covariates into the final model. Even these two has comparable performance. BIC takes much more computation time than SCAD and lasso. Let's get back to the beta carotene study. We consider a partially linear additive model by allowing the effect of age and cholesterol using the non-parametric terms. And we also wanted to identify some important predictors from this linear part.
So, excuse me.
Yes.
Just clarify to me. So the first issue is choose what you're going to be considered fixed and what you will not. And for doing that is the plots of the log beta carotene by the what make you decide that is age and cholesterol that you need to take care of?
Yeah, actually, this is a quite good question. So you are kind of to ask which covariates we should put in the linear part, which should be put in the non-linear part, right? So for this question, we have some suggestions. First, for some binary covariates, you definitely put it in the linear part, and for some, in terms of age or cholesterol, what we can do is you can kind of, like what we did, you can first fit a GAM, generalized additive model, trying to get an idea about the data. Then you kind of visually decide which one should be put in the linear part, which should be put in the non-linear part. And also since this is when you apply it to some real data, you need to also get some suggestions from some expert in that field, trying to give you some ideas how to build the models. So it's not an easy thing to do, but that's why we also wanted to consider whether we can create some test to decide which part the covariates should belong to.
Yeah, this may be a good point to ask my question. It's also possible to take data such as this and consider it as you're fitting a surface.
A surface.
And take a power series and all of the variables.
So when you
all the combinations of power series extension.
uh-huh. So when you say service, is kind of it to include multi-parameter non-parametric function, right? A function of multiple covariates.
I'm suggesting and want you to comment on an alternative model. Your PLAM has taken a set of linear functions and a set of unknown, possibly nonlinear functions. And in your process, you do an estimation procedure for the nonlinear part, which doesn't give you anything except an estimation of them. It doesn't give you parameters for it. So you don't know those. Okay. It would be possible.
There are parameters.
Yeah.
It would be possible to model log beta carotene as a power series expansion of the variables and fit that using standard techniques.
Okay, I see.
You could use all the linear terms, all the pairwise, the pairwise products, then the triples and so on. I've done this sort of thing in the past.
They're usually not numerically stable,
What?
right? The power series expansions are not numerically stable. That's why we go to B-spline basis.
Power series
They're
expansion
they're
one.
not usually numerically stable.
Yeah, it's
Right?
not
And so that's why you go to
stable.
B-spline basis. They're more numerically stable. And actually run.
So the thing is, the power spline is not stable. Then it's not as stable as the B spline.
All right, then answer me a question. When you said you fit the full model, how did you fit the full model?
You mean in my simulation?
In the previous data set, where you were dividing by the error from the full model, how did you fit the full model?
So you mean here, right? The full
Yeah,
model.
How did you fit the full model?
So the full model is we include all covariates into the model.
Including age and cholesterol.
Yeah, right. Right.
Did you estimate the coefficients for your age function?
Yes, since
How
we
did you
represent.
estimate the coefficients for age function?
Oh, that's because after the approximation, it becomes a linear model. So we can estimate coefficient in the splines.
In the PLAM, G1 is a sine function.
Yeah, they approximate that.
Yeah,
They
we approximate with some coefficients
Yeah,
times
well,
the basis
it's a
function.
sine function. When you fit the full model, how did you estimate the coefficients for the sine function in the model?
So what we do is use the.
You understand what I'm
Yeah,
She represented the sign
Yes.
as
Go back.
by a
There, right there,
spline.
right there.
Yeah, so the things
That's
we
what it
use
is.
this
So those
to
gammas are
represent the
coefficients,
whole
the
thing.
spline coefficients.
So you can think this is a new W here.
So when you said you did the full model,
When I did a full model, I put all X or whatever the cholesterol, not cholesterol, some beta carotene dietary, whatever here, and put two terms here. One is on age, one is, I should say, one is on age, one is cholesterol. Then I use a spline to approximate it. Then I calculate the BZ from observed age and cholesterol. So we get this part. So we only need to estimate the coefficients here.
And that you estimate by least squares.
Yeah, list the squares.
Basically, the spline approximation is
the
giving you an
spine
extra collection
approximations
of
within all
explanatory
used in
variables.
all of the computations.
Right, correct.
Yeah,
Correct.
the spline portion of it was used in all of the computations for all of the penalized models.
Right. Because it's never
And
subject
it's
to
the
selection,
same.
right?
So the spline portion is the same through all of them. So your
Yeah.
your penalty was only on the linear
Yeah.
parts
Right, right.
and using the same spline all the way through.
Yeah,
Okay.
yes.
And calling that the full model.
Yes, that's a full model. The full model means for the linear part, we put all
Okay.
covariates into it.
But
And
you
for
see,
the,
my question is, both G1 and G2 could also be estimated, say, in a power series expansion and left as parametric in the model.
yeah, right,
Yeah, that's what
right.
this is. It's just a
Exactly the
stable
idea here.
linear. It's more numerically stable.
Yeah, exactly the same thing here. So you suggest use a
It's not
power,
exactly the same thing.
you suggest the idea the same.
Well, it's a local
But
polynomial.
it's using them differently.
The basis function are
For this
different.
one, you're getting a numerical.
No, you're not choosing your knots differently. All you're doing is you're spreading your weight across the knots differently. That's all the B-spline does, right? It's just the way it spreads out the weight, and it localizes that, so you don't have weight on all the knots,
Yeah, okay.
which increases instability.
Okay, did that answer your question? So let me continue. So here I list the result from all these three methods, and also to compare it to the OLS estimate if we assume it's a linear model. And as we can see that SCAD identified all the four statistically significant covariates, and also include that the beta carotene dietary should be included in the prediction model. And compared to SCAD, Lasso included one more, the fat consumed per day into the prediction model, and the BIC just identified three covariates into the model for the linear part. So this result is also consistent to the simulation, the result from our simulation. That means BIC calorie tried to include less covariates into the final model, and the SCAD might be following it, and Lasso tends to include more.
So why do you think that's happening? I mean, why do you think SCAD is inherently, there's a finite sample here,
Yeah.
and we know that BIC tends to underfit, right, in finite samples. But SCAD has some problems too, right? You get this sort of the super efficiency stuff that happens, and don't you end up with similar problems where you can end up with too small models with SCAD? Is that true?
You're thinking the super efficiency stuff by
Posher
and
Lee.
Yeah,
And
that's
doesn't that map out in finite samples? You see strange results like
you
this?
can, but it's not peculiar to SCAD. It
No,
happens
I
with other
understand.
shrinkage methods.
But I guess I'm
Yeah.
surprised that you see such a difference between the BIC and SCAD.
Well, the BIC tends to impose more shrinkage than shrinkage methods.
Right.
And I think and I'm not surprised to see SCAD do best, in candor, because I've done simulations predictively comparing different shrinkage methods, and SCAD actually doesn't always win, but it wins most of the time, more often than any other shrinkage methods. The problem is that SCAD is often beaten by model averaging methods like stacking. So if you're going for prediction, I don't know why you do model selection first. And the other issue for why BIC might not be doing so well is the way she's chosen her spline basis, right? If you jack up the number of splines,
Then you're including that in your penalty term.
And you're including that in your penalty
That's what I was
term.
saying. It's kind of like, what impact does that approximation actually have?
it's going to make it more and more
Yeah,
unstable.
more and more conservative, right.
Well,
Okay.
it's going to make SCAD and Lasso, I
Yeah.
think, more unstable.
Okay, yeah.
That's what I would
Yeah,
expect.
but in terms of BIC, if you're now including all of those terms in the P part,
Oh, yeah,
Right, I mean,
yeah,
it's-
yeah. But then you're gonna have to be assigning priors, and,
Right.
and Vic is probably going to is gonna look for a variance bias trade-off.
but it's almost
Yeah.
like you're artificially making it more conservative than it needs to be.
Yeah.
And
But, that's because she's probably chosen a number of spline bases
Right.
to be too small,
Right.
and that's favoring scattered
Right.
lasso over
Right.
pick.
Right.
No, is that a fair?
Yeah.
I don't know.
That's
That would be my prediction.
Yeah, that's a good suggestion, discussion. So, one more thing here is remember that if we use the linear regression model, we cannot identify the effect of cholesterol, and the partially linear additive model can provide tools to also explore the effect of the non-linear effects. And more details can be found in our statistical cynical paper. Okay, so we can.
Yeah, could you go back to the previous slide? Yeah, I think this was a point I was trying to make and didn't make clearly. In the least squares, you have some information on age and log cholesterol. In the other, you really don't have it, although the influence is reflected back into the model. The influence of those two variables reflected back into your estimation. That's true. But you don't have information on any, because you've treated it non-parametrically, you don't have any information on its effect if you do it that way. That's what I was trying to.
We don't have information on.
It's kind of cumulative across those gamuts.
Yeah.
So you got to bring them all together and that approximates what this
You
one
can't
data.
compare your least square solution across the penalized methods for age and cholesterol.
Yeah, we can.
That's-
Yeah. So that's why I didn't
that's
list
why.
them.
That was the point that I was trying to get to.
Okay, thank you. So how many time do I have? Okay, so I just briefly discussed the extension to generalize the partially linear additive model. So since we allow Y to give the conditional distribution of Y given covariates belongs to exponential family, for example, to the Poisson distribution or Bernoulli distribution. And we can model the mean of Y, link the mean of Y to the predictors through some known link function. And here we also assume some partially linear structures on the effects of covariates. So for this generalized plan, we can construct the quasi-likelihood after approximation the non-parametric terms in order to get the estimate of the beta here for the linear part. And we showed the asymptotical normality of our estimate. And similarly, in order to select variables from the linear part, we introduce the penalty on the coefficients. And we also showed that the oracle property of our variable selection method, and more details can be found in this paper. So as a summary, we have proposed to use polynomial spline to approximate the non-parametric terms in a plan, and we have proposed to use scatter penalized RSS procedures to select variables from the linear part. And we also extended our approach to the generalized partially linear additive model. And we are now considering to extend our method to deal with high-dimensional data, and we will also consider to select variables for the non-parametric terms for the nonlinear part. And we also are considering to develop a test to decide whether the effect of covariates is linear or nonlinear. This will help us to build our model. And let me jump out of my talk and talk a little about my future research work. So in the past 5 years, I have mainly focused on 3 areas. variable selection Q models and some parametric regression models. And with my collaborators, we have proposed a variable selection method for the 3 semi-parametric regression models, and we are now also wanted to generalize our method to study the generalized partially linear single index model. And my work on Q model is like this. I have worked on variable selection for the proportional hazards Q model. This is a very widely used Q model, and collaborated with Dr. Huang and Dr. Han from Idaho State University. We developed a new Q model to consider both short-term and long-term effects, and we built a fully parametric Q model, and we are now working on to lose the assumption and build a semi-parametric version of it. And I'm also planning to develop variable selection for this new model and some other test procedures for the new Q model. And I'm also interested in longitudinal data analysis, such as some missing data problems, and also I'm interested in latent variable modelings. And since my work, it's not always a good idea to just select one models, then we might consider model averaging in order to get better predictions by pulling all models together. So that might be some future area I wanted to jump in. And I'm also interested in the application of statistics in cancer research or some psychiatry research. And also I'm interested in biomarker evaluation, especially for some genomic data analysis. Yes. I think that's it. Thank you. And I'd like to take any questions.